Welcome. Today's notes worksheet is entitled Transformations of Functions Day 2, and it's time to knock out transformations 7 through 10. We'll do it in the identical fashion to yesterday's lesson there, the 4 columns. So we'll get that going and fill that in, and then just do some follow-up examples and try to put it all together. So why don't we go ahead and dive right in here. If you remember yesterday, I took care of the notation, and then we kind of looked at the equations, the graphical consequences, and we named the transformation, all that good stuff. So right away, same thing as yesterday, if you can kind of think of it in this perspective, cause and effect. We're going to initiate a change on the equation, and what it's going to do is have some type of graphical consequence. And so that's what we're going to explore here. So let's get this going. 7 and 8 go together beautifully. 9 and 10 go together beautifully. We will be a little careful on 9 and 10 though. So here we go. We're going to introduce k for the first time. And so k times f of x. And these are going to be what are called our scale factors. For right now, everyone, all the way through 7 through 10, I'm going to keep my scale factors bigger than 1. And you'll see that phrased over the course of this lesson and in the practice problems too. So k is going to be greater than 1 for our interval here. And so let's start out with the basics. Does this look like an input change or an output change? And if you look at it, x is not being changed. It's f of x that's being changed by a factor of k. So this is definitely an output change. So not x, but f of x is being affected. And let's be specific about this. It looks like I'm going to multiply the entire function, so f of x. So multiply the function by k. All right, so that's looking pretty good right there. And let's go ahead and grab the graphing calculator. Maybe use some of those functions from yesterday's lesson to kind of put this together. So there we go. I've got it up and running. I'm going to go to my y equals. And I'm just trying to think, actually, which one would work good here. Oh, how about square root? Let's go with that one. So everyone type in square root of x. So that will definitely be our parent function. And what I'm going to do is take that parent function and multiply it by a number bigger than 1. So I'm just going to do a k value of 3. I hope that works for you. So instead of square root of x, I'm going to do 3 times the square root of x. And when I go ahead and do that, I'm going to hit zoom and number 6 at the top there. And we get that piece right there. Now in terms of the transformation itself, we need to be clear about a couple things, and then we'll see if we can get a good name on this. It is an output change as we have decided. And so in terms of the name over here, everybody, it definitely is something that is vertical in nature. Anything that is an output change is a vertical transformation. So if you kind of track this point moved here, this point moved here, this point moved here, etc., etc. Now, if you notice the difference, though, between yesterday and today, yesterday we talked about a vertical shift, where every single point moved up the same amount. But if you look at this, that is definitely not the case. They're not being vertically shifted. Anyone have an idea here? They're being vertically stretched, and that's going to be number 7. So the situation at hand here, let's get that in, is that those coordinates are being stretched away from the x-axis. I'm going to bring that up just one more time quickly here. Come on, there we go. So if you kind of look at it, these points are being stretched vertically upward. If I had points down here, they would be stretched vertically downward, so stretched vertically away from that x-axis. And what that means, of course, just you can write that in if you'd like, but I'm going to try to be specific. When we vertically stretch something, remember it's the y coordinates that change when we do something vertical. So basically I wrote it as every y coordinate is multiplied by k. So if you kind of think about this, take all the original y coordinates on the original function and multiply them by 3. And what they're going to do is stretch them away from the x-axis. I'm going to bring it up one more time just in case that verbal explanation doesn't register. So here's the deal. I multiply the y coordinate by 3, comes up here. Multiply the y coordinate by 3, comes up here. Multiply the y coordinate by 3, again, comes up here. If they were down here, you multiply them by 3, and they go further down. Outstanding. Okay, let's go get this one. Number 8. Very, very similar in its notation, but instead of k times f of x, I'm going to do it as 1 over k times f of x. So I'm going to keep my interval. Again, we're going to talk about these scale factors just kind of bigger than 1, so you'll see kind of a scale factor of 2, a scale factor of 3, a scale factor of 4. In this case, I would multiply it by either 2 or 3 or 4. Here, I would multiply it by 1 over 2, or 1 over 3, or 1 over 4. Hope everybody sees that. Same deal, guys. Let's go put this in. It is definitely an output change. No doubts about that. And just the only difference is I'm going to multiply the function by 1 over k. So that's all. That's the only subtle difference there. And what does that do? Well, let's see if we can put that together. So bring that calculator up, and let's go ahead and perform this transformation using my notation and my verbal description. So in this case, if I go scale factor, I used 3 up here. Why don't I do the same thing, kind of a scale factor of 3, but instead of multiplying by 3, let's multiply by 1 over 3. And so I'm going to do exactly that, guys. 1 over 3 times the square root of x. And I'm going to hit graph, and that probably could come up with a better window for this, but here was the original, and here is the new one. Obviously, it's not a vertical stretch. Sort of the antithesis to that, vertical compression. And that's the case for this one. Definitely output change, so you know it's vertical. And so this one, everybody, is a vertical compression. And so basically what happens, unlike the previous transformation, all of those points are getting compressed towards the x-axis. So it's getting closer and closer towards the x-axis. If I had some down here, they would be compressed towards the x-axis. So a vertical compression. And again, just kind of putting this all together, making sure the mathematics makes sense. But basically what I did is I took all those y coordinates again, just like I did before, and I multiplied them by the 1 over k. I mean, that's pretty much what the notation said. Take the function and multiply it by 1 over k. And so that's the issue at hand here. And think about what happens when you multiply these numbers by 1/3. Well, they become smaller. And if the y coordinates become smaller, they're getting closer and closer to the x-axis. They're being vertically compressed. Wow, that looks outstanding. So 7 and 8 now in the books. So if you rehash it, we have 4 shifts, 2 reflections, and right now at this stage, 1 stretch and 1 compression. Let's go get 9 and 10. Now 9 and 10, little harder. So let's go with number 9 first. So now the k goes inland. So there we go. K goes in. I'm going to still keep my interval the same, guys. Again, we'll just kind of talk about scale factors, 2s and 3s and 4s, et cetera there. And I guess I kind of gave it away. But does this look like an input change or an output change? And certainly, it is an input change. But remember how input changes work, everyone. Certainly different. So input changes is when we replace all the x's. So in this case, I'm going to replace the x's with kx. That's what I'm going to put in there. So as you can see, x gets replaced with kx. When we do that, let's see if we can name what happens. And then, of course, let's see if we can be specific on which coordinate changes and in what capacity. So let's get that calculator going again. Let's change families of functions here. So get rid of the square roots, if you don't mind. I like absolute value for this one, actually. So let's do this. Hit the math button. Go over 1 to the right. And this would be ABS. So do absolute value of x. And then go right on back into the y2 and do absolute value of, let's say, 2x. Let's do something like that. So all I did is I replaced my inputs with 2x. All right, now let's go ahead and hit graph. And there we have it. So this was the original. Let's go ahead and highlight that piece. This is the new one. There it is. And what happened to all those points? Well, the infinite number of points that made up the original function moved inward. So this moved here. This moved here, this moved here, this one moved here. So it looks like they're coming inward horizontally. And so, I think we have it. Unlike a shift, they are being compressed. So horizontal compression is number 9. So in this case, keep that in mind. When we replaced it with a 2x, didn't get stretched, it got compressed. And if you kind of look at it, let me see if I can sort of describe literally what's going on here. Remember, it's an input change. We all know that. So it's the x coordinate that's being affected. So if you kind of look at this piece, well, this point out here came in by a factor of 2. So what do you think? What am I doing to that x to make it become smaller by a factor of 2? To come in by a factor of 2. I wouldn't multiply it by 2, because if I multiply that number by 2, it actually comes out. So in this case, it looks like I'm dividing by 2, and that makes it come in. And so inputs and outputs definitely treated very different. So here's how I guess I would describe it. Every x coordinate is divided by k. So that is the graphical consequence of changing the inputs from x's to 2x. So those x coordinates come in by a factor of 2. So we divide by a factor of 2. That's going to be a tough one to wrap your mind around. I'll see if I can sort of summarize that maybe at the end of this lesson as to really why that works. But the way functions play out and the way you saw it, that is the case. Okay. Well, last one here out of the 10. And so let's get that notation in for you. You probably know what's coming. So something like that. Again, our scale factors, if I do a 2 or a 3 or 4, I'll just replace all my x's with like a 1/2 x or a 1/3 x or a 1/4 x. So 1 over k times x. So let's do exactly that. By the way, put an input right up here. And very simply replace all those x's with 1 over kx. That seems to be the situation at hand. Okay, so let's do that same family of functions. Let's do absolute value. Again, input, and instead of replacing that with a 2x, why don't we go right in here and replace it with like a 1/2 x, so a 1 over 2x. Again, scale factor of 2, but the way it is input into the function, it's going to be 1 over 2. So 1/2 x, and then let's go ahead and hit graph on that. Probably guess what's going to happen here, but let's go ahead and make sure. This is the original, and this is the new one. Now it looks like it's kind of coming down, but that's sort of just an overlap of what's really going on. It's really a consequence of the true transformation. So really, in reality, sorry about that. So in reality, what's going on is this point is moving out here. This point is moving out here. So they're moving outward, and when they do that, you can kind of see it looks like it's being compressed vertically. But in reality, the true transformation is that it is being stretched horizontally. So each of those points moves outward to the left or to the right. So the last one is what's called a horizontal stretch. Okay, good. And same scenario, we're going to actually put this in. Let me put it in now, and then I'll go back to that graph. But basically, every x coordinate is divided by k. I'm sorry, the 1 over k. So I'm going to go ahead and highlight that. But just kind of think of this in these terms. Dividing by 1/2 is really the same as multiplying by 2. So I'm going to write this, or multiplied by k. So remember how division works with fractions. Dividing by 1 over 2 is really the same as multiplying by 2. And when you multiply these by 2, they get further out. And so let's go ahead and take a look at that just so you can see. I know a couple of these points here, so maybe I'll try to highlight that. So here's one right here. I think that's probably 4, 4, give or take, right there. There's 4, 4 on the original. What happens is that point moves out by a factor of 2. So in terms of that equation, what I did is I put a 1/2 in, and we all know 4 divided by 1/2, so I divide by k. 4 divided by 1/2 is the same as 4 times 2, and so it comes out. And instead of 4 comma 4, hey, there it is, guys, 8 comma 4. And that's what happens for the infinite number of points right here. I keep dividing those x coordinates by 1/2, and dividing by 1/2 moves them outward. All right, well, we have 7 through 10 taken care of here. It's time to move forward. So let's do just the 2 types, equation examples and then graphical examples. So example 1, create a new function based on the transformation. Remember, a parent function can be anything, so there are some. And then what we're going to do is a transformation and come up with a new function right here. So let's start it out with letter A. First and foremost, horizontal stretch. The factor is 2. So as soon as you see the word horizontal, you know it's going to be an input change. So be very clear on that piece. What we did yesterday, and I'd encourage you to do today with these problems, is circle the inputs. So I'm going to change that input right there. And in order to pull this off, I do exactly what it said on the front side. I'm going to replace that input. In this case, if you read it carefully from the front side, horizontal stretch was the 1/k times x. So if it's a horizontal stretch factor of 2, what I'm going to do is replace it by 1/2x. Okay, so look at the front side if you're unclear about that particular piece. But that's how I do it. I replace the x's with 1/kx. And that should initiate the transformation that we're looking for. And so let's go ahead and clean this up. 4 times 1/2 times x. 4 times 1/2 is 2 times x. And I think that's our winner right there. So I'm going to graph this one. It's pretty easy to graph as you guys are processing that piece. But let's go ahead and take a look. I'm going to go ahead and get that. So 4x plus 1, and you should be able to envision 4x plus 1. And then how about a 2x plus 1? So the true transformation is that this has been stretched by a factor of 2 horizontally. So there we go. This point moves out horizontally by a factor of 2. This one moves out by a factor of 2. So they're moving away from the y-axis. Isn't that kind of cool? The closer they are to the y-axis, not so much of a move. The farther out, the bigger the change. So moving it out by a factor of 2. Excellent. All right, let's go get the next one. Letter B, horizontal compression, factor of 4. So the first thing I think of, that keyword right there, horizontal. So you know that one's a dead giveaway. It's an input change, of course. So circle those inputs, please. And the question, of course, becomes, how do I change those inputs? What do I replace those x's with? And so in this case, if you look at the front side, I replace those x's straight up with kx. So instead of x squared, it's going to be 4x squared. Instead of 2 times x, it's 2 times 4x. And that looks really quite good. So what we want to do at this stage is clean that out a little bit, remove those parentheses, please. I will ask you to do that, of course. 4 squared is 16, x squared, got that. And then here, 2 times 4x, and I think that's it right there. So what's going to happen is those points are going to come in by a factor of 4. They're going to be horizontally compressed. Okay, 2 down. Those are some tough ones right there. So let's be clear about how to work with those pieces in an equation, and then we'll take a look at the graphical piece. So separate them in your minds. Equation change, graphical change. Okay, let's go get the next. Letter C. So it's a vertical stretch, factor of 2. Anything vertical, of course, is an output change, which means we circle the entire function right there. The whole thing gets changed. And how does it get changed if we want to stretch it vertically by a factor of 2? Well, we take that whole function, and I basically just multiply it by 2. So that was the k times f of x, if you remember from the front side. Okay, good. And let's see, just want to clean this out, distribute that in. Just be careful, those are not grouping symbols, but absolute value symbols, so that's all I can do right there. But then the 2 times 4 gives you that. Not too bad. Removing those parentheses. Perfect. Okay, input versus output. Notice those subtle differences right there. And let's see if we can do 2. Let's see if we can maybe, just maybe, do it in 1 step. And if you don't like what I do up here on your screen, try to work it out in 2 steps. But I'm going to try to perform 2 transformations, everyone. I'm going to do 1 input change, so back to yesterday's lesson, horizontally shift it to the right by 1 unit. And then I'm going to do an output change. I'm going to reflect it over the x-axis. Input and output change. If we can do both simultaneously, great. If we can't, I would encourage you to probably do the input change first and then the output change second. So let's see if I can start this out a little bit here. I'm not going to circle anything at this stage. I'm just going to kind of deal with this piece right up here. Then I'll see if I can broach this subject right down here. So how do I move a function 1 unit to the right? You're going to have to know this from yesterday's lesson. And if you do remember, we're going to replace all of the x's, in this case those x's right here. I'm going to replace them with x minus 1. So instead of x squared, it becomes x minus 1 squared. Instead of a 2 times x, it's 2 times the x minus 1. So that right there would make the graph of this function move 1 unit to the right. I hope everybody remembers that from yesterday. Now at this stage, you are more than welcome to go ahead and FOIL this out, do this piece, and then do the next step. I'm going to try to consolidate if possible. So what I'm thinking here is then I also want to do an output change. I want to take that whole new function after this shifts to the right one, and I want to reflect it over the x-axis. How do I reflect something over the x-axis? I basically take the whole function and I put a big negative out in front. I basically multiply it by -1. Input change, output change. Do this to the whole function. It would be outstanding if you could pause the video and see either in my 1 step or your 2 steps, however you can do it, see if you can come up with the magical answer there. Okay, let's see what I get. I'm going to keep the negative for the time being. I get x squared minus 2x plus 1 plus 2x minus 2 plus 1. So that's that piece right there, just cleaning all that out. I see some good things canceling, by the way, minus 2x and 2x. I also see a 1 and a 1 and a minus 2, so these are all going to cancel out. Wow, goodness. All that's going. So I just get, here's my negative, and I just got it as that right there. And I'm going to go ahead and just multiply that by -1, so -1 times x squared. I don't know. I don't know if that's what you came up with. Maybe, maybe not. There's only one way to find out if I got it right. You know, kind of a moment of truth here. Let's graph it. So I'm going to go with my answer. I hope I did my math correct there as I look at this. And let's see. I have x squared plus 2x plus 1. There is your parent function. I want to move that 1 unit to the right and also flip it over the x-axis. And apparently, to do that, this would be the function that would make that happen. Let's see. Oh yeah, that looks great. There's the original. It moved 1 to the right and flipped. There you go. Okay, so you have 10 transformations to work with. At this stage, everybody, I should be able to give you any function, represent a parent function. I should be able to name any of the 10 transformations, and you can tell me the new function to make it happen. Cool. Let's go forward. So we've done this one, just tracking a singular point. So let's go for it one more time here. Let 5, -4 be a point on the function y equals f of x, so on the parent function. Determine the corresponding point based on the transformation. All right. I don't know if I left you enough room here, but see if you can go ahead and give me a coordinate plane. I'm going to try to do this justice over here. And go ahead and plot, what's that, 5, -4. 1, 2, 3, 4, 5, 1, 2, 3, 4. Big old point right in there. So that represents a singular point on the graph of a function. Where does it go after I initiate the transformation? So the first order of business, looking at these 6, is you have to be able to identify which of the 10 transformations it is based on the notation that you see on your screen. So let's start it out. Alrighty, 2f of x, number bigger than 1 times the function. Again, it's vertical without question because it's an output change. And if you remember from the front side, if it's bigger than 1, it's going to stretch it. So it's going to be a vertical stretch by a factor of 2. And so you can keep going back and forth here, front side and back side. I've got these pretty much laid out. But basically what we want to do is, if it's vertically stretched, the x-coordinate stays the same. Let's be very clear about that. It's just that y-coordinate that's going to change. And how does it change? Well, if you remember, I just take the y-coordinate and to vertically stretch it to make it go further down, I multiply it by 2. And so it should move down here by a factor of 2. That would move it away from the x-axis. And instead of 5, negative 4, should be 5, negative 8. Good. And if you look under the graphical description of vertical stretch, that's what should happen. Okay, this is definitely a tough one. I'm glad I threw this in right away here. So which is this? Well, it's definitely horizontal, so I will put that on my board right here. And then, what do you think? Is it the stretch or is it the compression? And if you remember, the 1 over k is the stretch. So this is one we're going to have to be very careful with. It's going to be horizontally stretched, meaning it's going to move outward. It's going to move somewhere out here, wherever it may be. And it's going to move out, it looks like, by a factor of 2. So first and foremost, let's get this going in terms of our ordered pair. If I horizontally stretch it, it doesn't affect the y. Again, horizontal. Only x is being changed. Well, how do I get it to be stretched? Well, the x-coordinate is going to have to get bigger, right? Don't make it smaller because that would be a compression. So you have 2 options here. What it says on the front side is take your value, your x, and divide it by 1/2. What's another way to think of dividing by 1/2? Well, multiply it by 2. And so 5 divided by 1/2, or 5 times 2, is 10. And so that, if you can picture it, 10, negative 4, now stretches it out here by a factor of 2. Awesome. Okay, so horizontal stretch, make it happen. Next one, everybody, when the negative's on the outside, it's one of the reflections. Is it x-axis or is it y-axis? In this case, if you remember, should be an x-axis reflection. Because what's going to happen is I'm going to take my y-coordinate and change it to its opposite, exactly like that, exactly what it says. This one is an output change for sure, so the x stays the same. Again, look at that notation, output change, not input. So keep 5 the same. How are you changing the output? How are you changing the y's? Well, I'm basically changing everyone to its opposite. So in order to reflect it over the x-axis, make it come up here. Well, basically it changes from negative 4 to its opposite. Okay, good. 3 down, 3 to go. Let's get the remaining ones. This one matches that one. Vertical. Looks like a 1 over k times f of x. And in order to make this one happen, I'm seeing it as a vertical compression. Good. So make sure you do it in the exact same way here. Again, vertical compression means x stays. It's just getting vertically compressed, meaning it's coming closer to the x-axis. It's coming upward, basically, here. And so that y-coordinate's going to get smaller by a factor of 2. So what we said is just take the y-coordinate and multiply it by 1 over k. Half of negative 4 is negative 2. And so you can kind of see that right here. It had to come up by a factor of 2. So I basically multiply that by 1/2, or divide by 2 if you want to think about it that way. And so there it is, vertically compressed. Good one here. This is a horizontal shift, I will tell you that, for letter E. Here's the good question. Left or right? And by changing the input from x to x minus 3, it goes to the right. So it is a horizontal shift to the right, and all you want to do is literally count 1, 2, 3, put a point, and you can kind of figure out that piece. Again, input changes are rather weird, but that would be what happens here. And again, I think right at the end of the lesson, I'll probably have just a moment or two kind of talk about really why that is, why that works. And in this case, though, as we saw graphically, minus does move it to the right. And if I move it to the right 3, the 5 moves over to the 8. Cool. And last of this set right here, let's go get this. It's definitely an input change, so it's horizontal in nature. And what do you think on this end? I'm hoping you said compression. So horizontal compression by a factor of 5. So in this case, kx, it's going to come inward by a factor of 5. There we are. Actually, this one comes inward by a factor of 5. So basically what we said, to make that come in by a factor of 5, I would divide the x-coordinate by 5. So first and foremost, the y-coordinate does not change. If I want to make it smaller by a factor of 5, well, very simply, I take 5 and divide it by 5, and I get that. There it is. It came inward, so it has to become smaller, and so I take that x-coordinate and I divide by 5. All right, it's a lot to wrap your mind around. There's some really interesting transformations here, and again, 10 of them to deal with, so a lot to cope with. All right, good. I'm going to move on to my next piece, and let's just graph a couple, just using the concept of transformations. Doesn't have to be perfect by any means, but just really solidifying what you see in terms of the transformation. So this is a quadratic, and I guess here's what I'm going to have you do. I don't know if this is going to be perfect or not. In fact, I think I'll come right down here, and I'm just going to use the most basic quadratic function. Let's just do y equals x squared, and just put a little 1 out in front if you don't mind. And what I want us to do is just graph y equals x squared, and it doesn't have to be perfect, but you know, it probably would look something like this, give or take. So there's my parabola. And I'll tell you what, why don't you just put a little 1 right above that, something like this, and I'll go ahead and do that. So there's your 1. Let's circle that. Maybe that's better. So there's your 1. Okay, now I guess I would ask you is, what are the transformations to get from the parent function to this right here? We'll take one at a time. And again, I would do input before output. So what do you think? Let's change. In this case, it was x squared. What do you say we go with that input right there to x plus 4 squared? So, by the way, if you can do this in one shot, that's great. I have no problems with that. But let's just go one transformation at a time, at least up here, and then see if it makes sense. So what do you think? From here to here, replacing the input, replacing the x's with x plus 4. What does that do to the graph? And what it should do is take the infinite number of points on the graph of this function and move it to the left. So 1, 2, 3, 4, and I get the exact same parabola, just looking like this. So I'm going to go ahead and put a little 2 on that guy right there, and that's it. That should be it right there. Okay. Now, number 3. Let's go further. Let's initiate the secondary transformation. That was the minus 2. So that was, now take that graph, and let's go ahead and throw a minus 2 behind it. So here was my function from the previous step, and now it's the exact same function, except it's a minus 2. Which of the 10 transformations does that represent? And I'm hoping you would all agree that just tells me to go down 2. So this is not going to be perfect, but I'll do my best here. Let's go down 2, and should look something like this right here. And let's just put a little 3 on that. And so left 4, down 2 from the original. Input change, output change. I'm not going to, just I'm looking at the time frame here, but I would encourage you to graph the function. So graph this piece right here and see how well we did. And it should pretty much be spot on. Okay, letter B. So let's do the same exact thing, everyone. This one off the cube root function. And again, we don't have to point plot here. That's not really what I'm looking for. But I know some of these graphs pretty well here, so this one's going to look something like this, give or take. So there's your y equals cube root of x. Try to throw that into the mix if that's all right with you. And in this case, I actually, from my perspective, I see two output changes. And so let's go ahead and be clear on that piece. In this case, it's got a sort of the multiplication of 4 and then also the addition of 3. Well, you know, order of operations always tells us to do multiplication first. So why don't we go from cube root of x to 4 cube root of x? And what do you think? Which of the 10 transformations is it? Again, it's not an input change. I didn't change that. I changed the function by multiplying it by 4. And if you remember from the front side here today, this looks to be vertical and it looks to be a stretch. So basically what happens is all of these points get stretched by a factor of 4. So I'm going to go ahead and I know a couple of them, so I'll at least get that started. This moved up by a factor of 4. This moved down by a factor of 4. And so, you know, again, not going to be perfect here, but basically should look something like this. And that's nice. So stretched by a factor of 4. Vertically. Cool. Now number 3, the secondary output change. So what happens when I do that 4 cube root of x and then just, let's throw ahead and a plus 3 on the back. And what would that do? Well, of course, I think we all know that is a vertical shift upward. So we just take all the points from here and move it up 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, etc., there. And again, just to the best of your ability, let's get that going. And that's number 3. And that's it. And I think you would find if we graphed this function right here just straight up, should produce something along those lines right there. So I'm hoping it's really starting to click, just all the ways that the equation change sort of affects the graph, and trying to put that in place one step at a time. Okay, very good. Let's go to my last board right here. All right, let's reverse. So example 4. Use the concept of transformations to write a function for each graph. So first and foremost, I will tell you this one right here is in the cubic family. And you don't have to do this if you don't want to. I'm going to do it up here. Essentially, let's go ahead and sort of draw this in. There we go. So that would be my y equals x cubed, just FYI. And so what I'm looking for is the equation to match this graph right here. So think of the transformations. A couple ways I see this, by the way. But look at the transformations and then see if you can create that from the equation. So this would be great if you could pause the video and pull this one off. Okay. Well, you know what I saw? I saw just taking this graph and literally the whole thing, move it 2 units to the left. And then it looks a little different, but after you move it 2 units to the left, it would look kind of like this. I'm going to just outline it for you right there. So that would be 2 units to the left. And then if I flip it, I'm thinking of it as an x-axis flip, because these would come down, these would come up, and then I've got it. So I see those two things happening. I see moving the original graph left 2 and flipping it over the x-axis. And so in order to do that, here would be the left 2. Instead of x cubed, it's that x plus 2 cubed, and that would be a flip over the x-axis. Okay, I'm going to graph this one. We do have a moment here, so I'm going to go ahead and do that. Let's just see. So negative x plus 2. And by the way, it's just, you know, when I give this to you to do on your own, perfect way to see if you got it right. Just graph it. Yeah, that looks great. Cool. Let's go get letter B. And so I will tell you this is off the square root family. Same deal, everyone. Square root looks something like this. That's y equals square root of x. I will tell you, I remember putting this in. There is a stretch on this one, just FYI. So think about the transformations to get from here to here. And can you create the equation that does it? All right, well, let's see. Either you did it or not, whatever the case may be, but I'm seeing this has to reflect. This has to come over here. So I'm seeing a y-axis reflection, which would kind of be this. And then it looks like from there, it's not shifted, because that point is still staying right there, by the way. It looks like it's stretched. And I've got it stretched kind of by a factor of 2, because originally it would be right here, and then, but if you multiply it by 2, it comes up here. Same here and here. Yeah, just I see that as the scale factor. It looks like a 2. So let's do that y-axis reflection first. Square root of x initially. Now it's the square root of the opposite of x. Change the input. And now, also to include the vertical stretch by a factor of 2, it looks to be that piece right there. I think that's it. Let's go ahead and check that out. So one more time here. I've got a 2 square root negative 1x. Good to go. And that's it right there. Awesome. Now, at this stage, I would encourage you to do one of two things. You can either stop the lesson at this point if you're kind of satisfied, you're ready to roll on some of the practice problems. If you want to just see a couple more things, especially on the inputs, you know, y minus moves it to the left, y plus moves it to the right, y, the bigger number with the horizontal is a compression, and y the 1 over is the stretch. If you want to do that, hang on to the video for like 2 minutes here. Otherwise, as I said, you can just stop it and be done with it. So here's what I'm thinking. Just a quick explanation on those inputs, because I think it really does make a difference. I'm going to just start with an input, everybody. I'm just going to start with basically an input-output situation. And functions work, as we all know, like this. Input produces output, right? And so what we want to do here is think about what happens when I change the input. Weird things occur. So think about this for a second. So what happens if I change all of my inputs from x to x minus 3? Well, what that would mean for this particular situation is that I have to get to the 6 in order to make an output of 4. So if you look at this piece right here, everybody, what would be my new x value in order to get this to be 6? Well, if you think about it, the new x value would have to be 9, right? 9 minus 3 is 6. Then this is the input. This 6 is what produces the 4. So in reality, when I do this, that input had to change from 6 to 9 with that minus 3 there. And think about this. Is the 9 to the right or is it to the left of 6? It's to the right. And so that's the situation. That's why minus moves it to the right. The more we subtract here, the further to the right this has to get, because I have to get this in order to produce that. Again, how about one more right here? Something like this. What if I changed all the inputs to x plus 2? Well, for this particular case, again, I have to get to the 6. What plus 2 will give me 6? It's 4 plus 2. And is 4 to the left or is it to the right of 6? Well, 4 is to the left. So the greater we add here, the more this goes to the left. The new x value is to the left. So instead of 6, 4, it would move to 4, 4. That's how it works. How about the compression and stretch situation? What if I did something like this? Some people think that this is a horizontal stretch, but it's not. Because if you think about the way functions work, I have to get to the 6. Hey everyone, 2 times what would give me 6? 2 times 3. And is 3 farther out or closer into the y-axis? It's closer to the y-axis. It's smaller than what we have here. The bigger this scale factor is right here, the smaller these numbers get, the smaller the new x values. So from 6, 4, it goes to 3, 4. That's why we take, if you remember the graph, I take my original x, divide by 2, that gives you the new x. Same thing, last one. What happens when I do that? What does the new x have to be? Well, when I do my 1 over 2, half of what would give me 6? Well, half of 12. And so now the new x value is 12. Sorry about that. So anyway, I think I was saying something like the new x had to be 12, which is definitely stretched away from the y-axis there. So this one is certainly a horizontal stretch. So hope that kind of solidifies some ideas there. But you're going to have to know those 10 transformations pretty well. Let me know how I can help you with that. Please, again, don't hesitate to ask questions. And thanks for listening to the lesson.